Right, the moment's question 13. A couple of you got in touch with me about this, saying this was really hard. But it's not as challenging as maybe you initially thought. Admittedly, the diagram is quite complicated. There's a lot going on. There's certainly quite a few forces going on. So I think that's what kind of put you off. But once you kind of like delve into it, it's not that challenging at all, to be honest. So let's have a little look. Right, first part, it wants you to basically derive this expression here. Now, when things are in equilibrium, okay, there's two criteria that have to be obeyed. The first criterion is that forces must be balanced, and the second criterion is that the moments about any pivot must also be balanced. So they are the two separate criteria for things to be in equilibrium. Now, this first expression here is actually about forces being balanced. Right, now we have to take the direction of R. So let me just draw right, let's take the direction of forces in this direction. Okay, so let's take the direction of forces to be perpendicular to the slope. Okay, now hopefully you can see there that we have two lots of R going up, but we've got two weights going vertically down. So what we need to do, we need to find the component of the two weights, the weight from the backpack and the weight from the man. There they are there, W and 740. We need to resolve them and find the components in this direction. Okay, we need to find the components of those two weight forces in the same direction as R. Okay, so that's what we need to do. So let's just tidy up the diagram first. So it's as simple as that, really. Right, so the two R's are going up perpendicular to the slope. So we can start with that, can't we? Blue. So 2R. So that's the force, the total force upwards. When I say upwards, I mean an angle upwards, but perpendicular to the slope. Now the two forces pulling down. Okay. Right, well, we've got two, haven't we? We've got the component of W and the component of 740. Right, now if I draw this like this. So we're going to have that component there, and we're going to have this component here, aren't we? Okay. Now, what angle do we use? If this angle here is 20 degrees, then this angle and this angle are also 20 degrees. So the components of W and 740 have a cos 20 degrees in them, don't they? Okay, so then we're just saying, well, the total force downwards in the opposite direction to R is going to be this component plus this component. So the W component is W cos 20, and the 740 component is 740 cos 20 degrees. Take the 2R over to the other side, and hey presto, we have this expression here. Okay, fairly straightforward, that bit. Now, that's why it's worth 2 marks. Anyway, right, so it gets a bit more complicated now. Now, thankfully, not all questions will do this, but thankfully, it actually draws a free body diagram. Okay, it just draws the forces, because like I said before, there's plenty of forces going on here. Look, we've got frictions parallel to the slope. We've got two reaction forces pushing through the feet, we've got two different weights. Okay, so quite a lot going on. Now, it wants us to take moments, doesn't it? Now, like I said, it does signpost the thinking quite a lot. It tells you to take moments about O, which is quite convenient because look, if we take the moments about O, that immediately eliminates both frictions because they both pass through O, but it also eliminates one of the R's as well. So if we take moments about O, we only have to consider the W force, the 740, and that reaction. We've only got three forces to play with our moments calculation. Okay, now we have a slight complication in the fact that these two forces and these two forces are not parallel. Okay, now we could resolve the distances, but I think it's much more straightforward to resolve the vectors. Let's get all the forces perpendicular to the slope. So we just need to resolve now two forces, don't we? Like I did in the previous question. Okay, so let's have that component and that component, like I said, exactly like we did in the previous question. Like that. And they're the ones we're going to use in our moments calculation, which makes it quite convenient because we only have to use these distances. I think that's a lot more straightforward doing it that way. Okay, right, so let's just remember what's this component. This component is the component of W is W cos 20. Cos 20 is 94, so this is 0.94W. Okay. Now, 740 cos 20 is 20 cos times 740. 20 cos times 740. 695. So 695 newtons. Okay. Otherwise, we're going to get a lot of. If we just leave the cos 20s, it's the actual equation is going to get quite complicated. So I always like to actually calculate things out. If we, rather than leaving all the causes and the signs in there, it can get quite messy. Okay, right. So there's our forces. Like I said before, the three forces producing any turning effect about O, or this one, and this one. Right. Moments about O. Okay, let's do anti-clockwise first. Right, which of those three forces is producing an anti-clockwise moment? Well, that one, quite obviously, but also this one. This is producing an anti-clockwise moment. This force and this force are both trying to topple the hiker backwards. So we have clockwise moment. We've got 0.94 W times perpendicular distance, which is 0.10, plus R times 0.40. Make sense? So that's those two forces, those two moments rather, added together are producing the anti-clockwise moment. Okay, clockwise moment, we have 695 times 0.25. Okay, so we've got that force there. This is producing the clockwise moment times 0.25. So 695 times 0.25. Okay. Should be a bit more straightforward now. All we have now is two simultaneous equations. We have this one where W and R are unknowns, but we also have, don't forget, this one where W and R are unknowns. So it's just a fairly straightforward simultaneous equations exercise now. Okay. We want to eliminate R, don't we? Because we want to find W, we want to eliminate R. So let's go back to this equation here. We can just tweak this equation. R comes if we divide both sides by 2, we get, this is 0.47, and then this thing divided by 2 is 348. So there we have it. So we've got an expression for R, which we substitute into here. Okay, we have an expression for R, which we substitute into there. So just to thrash this out for you, we've got 0.94 W times 0.1 plus 0.4, 0.47 W plus 348 equals 174, not 174, but 174. Okay, so there we have it, an expression which just has one unknown in it, and that comes out, that gives us a W of 124 newtons. There you have it. Okay, not as scary, I think, as it initially maybe seems. All right, last little question though. It wants to know, hiker repacks his bag, placing heavier items at the bottom. Explain why this might cause R on his front foot to decrease. Right. If he packs heavier items towards the bottom of his bag, what's that going to do with the center of mass in the bag? Okay, right. Because the bag is at an angle like this, if we pack heavier items towards the bottom, the center of mass is going to be moving in that direction, isn't it? The center of mass is going to move away from the pivot. If the center of mass is going to move away from the pivot, okay, then this force here, this force is going to move further away from the pivot. If this force moves further away from the pivot, it's going to produce a bigger anti-clockwise moment. So if this force here, the weight from the backpack, produces a bigger anti-clockwise moment, that means the anti-clockwise moment from this R has to decrease. You can't have the anti-clockwise moment from this force and this force both increasing. If the moment due to this force goes up, the moment due to this force must go down. And the only way the moment of this force goes down is if the value of R decreases. I hope that makes a bit more sense. Right, thank you very much.